Okay, class, good morning. So again, this is the continuation of the performance of diesel power plant. So this is part 3 of the presentation. Okay. So by this time, we are now going to discuss the thermal efficiency of the engine. So thermal efficiency, it is the measure of how much energy input is converted into an output. So this thermal efficiency is divided into four. Okay. First is the indicated thermal efficiency. So meaning you are going to look for the thermal efficiency inside the combustion chamber. The next is brake thermal efficiency. Next is the combined thermal efficiency. And the last one is the plant thermal efficiency. So basically, thermal efficiency is equals to, of course, the output divided by the energy chargeable to the engine. Okay? So, designated as E equals to P, or the power, divided by the energy chargeable. Okay. So, let us now proceed to the indicated thermal efficiency, designated as EI. Okay? So this is the ratio of the indicated power to the energy chargeable to the engine. Okay? So from the equation, EI, or the indicated thermal efficiency, equals to indicated power over energy chargeable. Now, substituting the values where the energy chargeable is equals to the mass flow rate of the fuel multiplied by the heating value. So, multiplying this by 100%, so the answer for this efficiency is in percent. Okay. So, looking at now the units involved in this efficiency. So, we know that power, that is defined in kilowatts, horsepower, or PS, the European standard. Okay? And also, the mass flow rate of fuel is defined in terms of kilogram per hour. And the heating value, that is defined in kilojoules per kilogram. Okay? So, knowing also that kilowatt is also equal to kilojoules per seconds. Kilowatt, okay? Kilojoules per seconds. And then substituting it to the equation and then converting the number of seconds here to hour. So that is equivalent to 3,600 seconds. Therefore, the formula now for thermal efficiency is equals to 3,600 multiplied by the indicated power over the energy chargeable, or MF, multiplied by the heating value of fuel. Okay? So, another, we have the brake thermal efficiency, AB. Okay? So, another, this is the ratio of brake power to the energy chargeable. So, the derivation of the formula are the same, of course. So, in the previous slides, so for indicated thermal efficiency. Also, the derived equation for the brake thermal efficiency is 3,600 multiplied by the brake power over energy chargeable, or MF, times AB multiplied by, or heating value rather, multiplied by 100%. Okay? So another, we have the so-called mechanical efficiency. So that is in between the indicated power and the brake power. So, mechanical efficiency. So, this mechanical efficiency is an efficiency due to the friction losses of the engine. So, of course, the higher the mechanical efficiency, the higher the brake power develop. Okay? So, substituting now from the formula, mechanical efficiency is equals to brake power over indicated power. Okay? So, that could now be equal to the brake thermal efficiency or the brake power or the brake thermal efficiency multiplied by the energy chargeable over EI multiplied by EC. Okay? So, we just substitute the brake thermal efficiency. Okay? So, mechanical efficiency now is equals to the brake thermal efficiency divided by the indicated thermal efficiency multiplied by 100%. Okay? So that is mechanical efficiency in terms of the indicated thermal efficiency and the brake thermal efficiency. Okay, class? So another, we have combined thermal efficiency. So combined meaning this is after the generator output. So we are looking for the output of the generator here. So the combined thermal efficiency is defined as the electrical power or the combined power divided by the energy chargeable multiplied by 100%. So substituting values here where AC equals to MF times HB, thermal efficiency now or the combined thermal efficiency equals to 3,600 multiplied by the electrical power or the output of the generator over energy chargeable, where energy chargeable is again MF multiplied by HB multiplied by 100%. Okay? So, another here is the plant thermal efficiency. So, meaning we are now looking for the plant output here. So, instead of electrical power, so we are going to multiply that electrical power by the factor 1 minus percent plant used. Okay? So, the plant thermal efficiency now equals to electrical power times 1 minus percent plant used over AC. Substituting again the values, the plant thermal efficiency now equals to 3,600 EP multiplied by 1 minus percent plant used over MF times HB multiplied by 100%. Okay? So, let us now consider an example. So, for this presentation or for the topic in this presentation. Okay? A two-stroke four-cycle cylinder, four-cylinder 384.2 millimeter by 533.4 millimeter diesel engine is guaranteed to deliver 522.2 kilowatts at 300 RPM. Okay. The fuel rate is 0.255 kilogram per kilowatt hour. If the heating value of the fuel is 44,316 kilojoules per kilogram, calculate, okay, brake thermal efficiency, brake mean effective pressure, suction displacement, and cubic meter per minute. So that is for shaft power. Okay. So heat supplied to the cylinder per cubic meter displacement. Okay. So given number of stroke is 2, number of cylinder is 4, diameter of the bore is 384.2, the length of stroke is 533.4. The power is 22.2 kilowatts. Number of RPM 300. fuel rate of 0.255 kilogram per kilowatt hour, and a heating value of 44,316. Okay, so determining now the mass of fuel. So knowing that mass of fuel, the fuel rate is equals to the mass of fuel divided by the power. Okay? So substituting values, the mass of fuel now required is 133.161 kilogram per hour. Okay? So for brake thermal efficiency EV, okay? EV is equals to 3,600 times BP over energy chargeable or MF times HB times 100%. Substituting values, the brake thermal now is equals to 31.8%. And then solving for the brakeman effective pressure. So from the brake power formula, okay? Brake power formula is BMIP times LAN over 60 for SI, okay? So getting now the value of BMIP or the brake main effective pressure, the value is 423 kilopascal. So getting now the piston displacement, so that is BD is equals to LAN, substituting values, and then converting millimeter to meter, BD now is 1.237 cubic meter per seconds. For the suction displacement is equals to 1.237 divided by the power. So the basis here is the brake power. Okay? So that is why the suction displacement is 0.142 cubic meter per kilowatt minute. Okay? Thank you very much. So that ends my presentation in this part 3 of the discussion. Thank you very much.